Welcome to day 8 of our 10-day short course program on metrology and mechanical measurements. Today's session primarily focuses on calibration and traceability along with the industrial case studies. Our objective is to understand how calibration, traceability, measurement, uncertainty, and environmental conditions influence the accuracy and reliability of industrial measurements. Let us begin with a quick recap of measurement traceability chain. Every measurement made on the shop floor should be connected through an unbroken chain of calibrations to a recognized national or international standard. The chain progresses from SI units to national standards to an accredited calibration laboratory and finally to the measuring instruments used in practice. Now let us move from theory to practical industrial situation through 4 important case studies. This is our session roadmap. So case study 1. Our first case study concerns with digital vernier caliper used for dimensional inspection of machined shaft in an automotive component manufacturing environment. Although the calipers appear to indicate 0 correctly, inspection reports showed shaft diameters consistently oversized by approximately 0.03 to 0.05 mm when compared with CMM inspection. The root cause was calibration performed only annually, while jaw wear and battery-related zero drift remained undetected. The corrective action was to introduce daily zero checks using a gauge block, reduce the formal calibration interval to 6 months, and clearly identify the calibration due date on each instrument. The key lesson is very simple. A calibration certificate represents the condition of an instrument at a particular point in time. Routine interim verification is therefore essential for detecting final drift before it affects the customer. The next case study is about calibration of pressure gauge. Our second case study comes from a chemical process plant where Bourdon tube pressure gauge were used to monitor the reactor pressure. During an audit, 3 gauges failed the acceptance criterion. One gauge was reading approximately 8% low near the upper range limit, creating a potential safety risk. The investigation showed that calibration had been performed at only one mid-scale point. The hysteresis and non-linearity errors at other points were not adequately evaluated and vibration effects were also ignored. The corrective action was to introduce 5-point calibration at 0, 25, 50, 75 and 100 percentage of the range together with as found as left records. The important lesson is that single point calibration can hide significant errors elsewhere in the measurement range. Calibration should represent the actual operating range of the instrument. The third case study focuses on RTD sensors used in pharmaceutical applications, including sterilization processes and cold storage facilities. An internal audit revealed that some calibration certificates were not traceable to a national metrology institute. The reference used by the sub-vendor itself was not adequately calibrated. The root cause was the selection of a low-cost calibration service without verifying the ISO accreditation and without checking the traceability chain behind the certificate. The corrective action was to recalibrate critical sensors through an accredited NABL laboratory and introduce traceability verification as a mandatory part of vendor qualification. The key message is traceability is only as strong as it is as its weakest link. Never evaluate a calibration certificate merely by its appearance or existence. Verify the accreditation and the reference standards supporting it. Our fourth case study comes from the aerospace manufacturing sector. A bridge-type coordinate measuring machine was used to inspect the turbine brackets with very high tight tolerances of approximately plus or minus 5 micrometers. A batch of components passed the manufacturer's CMM inspection but subsequently failed dimensional verification at the customer's accredited laboratory. The root cause was thermal expansion caused by uncontrolled environmental temperature variations. The CMM software did not adequately compensate for these temperature changes. The corrective action included relocating the CMM to a temperature controlled metrology room maintained at 20 degrees Celsius plus or minus 0.5 degrees Celsius, enabling thermal compensation and introducing environmental logging. The lesson is extremely important. Measurement accuracy depends not only on the instrument but also on the measurement environment. Now let us have a comparison between all the four case studies in common sense. Across manufacturing, process industries, pharmaceuticals, industry, and aerospace, a common pattern emerges. The problem was not necessarily a defective instrument. Instead, the failure resulted from gaps in the calibration interval, calibration method, traceability chain, environmental control, or verification process. There are several common pitfalls that organizations should avoid. First, do not depend blindly on fixed calendar based calibration intervals. Second, never rely on single point verification when the instrument operates across a wider measurement range. Third, verify the accreditation and traceability of calibration service providers. Fourth, control environmental influences such as temperature, vibration, and humidity. Fifth, conduct simple interim checks between formal calibration cycles. And finally, maintain proper documentation so that measurement drift can be identified over time. A strong calibration program should be based on risk, actual drift history, and instrumental usage rather than routine assumptions. Measurements should be verified across the full working range. Calibration vendors should have appropriate ISO accreditation and traceable reference standards. Environmental conditions should be controlled and recorded. Interim verification should be performed between formal calibration cycles, and both as found and as left data should be documented for future analysis. Let us conclude our today's segment with five important key takeaways. First thing, measurement failures often originate from gaps in the calibration process or traceability chain rather than from a faulty instrument. The calibration intervals and verification points should reflect actual risk and operating conditions. Traceability must be verified from end to end, including the accreditation of calibration service providers. Environmental control is an integral part of reliable measurement. Good documentation transforms a calibration certificate from a static record into useful information for monitoring measurement drift. Remember our key message: accurate measurement begins with calibration. Trust is built with traceability. So with this few key message, thank you for participating in day 8 of the short course program on metrology and mechanical measurements. Thank you, and I look forward to your participation in the next subsequent session. Thank you all.